Okay, good morning, afternoon, or evening, everybody. Welcome to the NASA Globe Clouds, Matching Cloud Observations from Citizen Scientists with NASA NOAA Satellite Data webinar. This is your host, Jennifer Brennan. While everybody is logging in here, some of you have already noticed, but we do have a few optional polls located at the bottom of your page, and I'd like to thank all of you in advance for your feedback on these polls. What I'd like to do first is review a few logistics related to this webinar. To ensure the best audio experience, the conference has been placed in silent mode. However, if you have any issues or you have any questions, what I'd like for you to do is enter those into the Q&A pod, and you can find this located on the lower right-hand side of your screen. This works like a chat. Today's webinar is being recorded. The recording will be posted both to our online Adobe Connect webinar catalog as well as to our NASA Earth Data YouTube channel within a couple of days of completion. And what I'll do is I'll send an email to all registrants that will include the recording links. In addition, today's presentation files will be available for download at the end of the webinar. As far as timing is concerned, today's webinar is 1 hour long. We've allocated 45 minutes to the presentations with additional 15 minutes for the question and answer period. Once our speakers have finished their presentations, what we'll do then is we'll move to an optional final set of polling questions, and then we'll give those a couple of minutes, and then from there we'll move directly to the Q&A period. And then just a final note, depending upon the volume of questions we receive today, we'll extend the Q&A period an additional 15 minutes to 3:15 p.m. for those of you who may wish to stay on the line. And what I'd like to do next is pull up today's agenda. Excuse me. During today's webinar, we will have 4 speakers. Our first speaker is Marilei Colon-Robles, who is the project manager for the NASA Globe Clouds program. She'll start off by providing a history and introduction to Globe Clouds. And then from there, we'll transition to our second speaker, Tina Rogerson, who is a data programmer or analyst for the Globe Clouds team. She will discuss how these citizen science data are being collected and also processed. Our third speaker today, Dr. Brant Dodson, is a research scientist on the Globe Clouds team. He will then lead in with a discussion about the possible scientific uses of the And then finally, our last speaker today is Kaylee Dantas, who is a data science intern on the team. She'll present some information about the future direction for this project with the use of neural networks. With that, it is my pleasure to introduce today's first speaker, Marilei Colon-Robles. Marilei?
Hello, everybody. Thank you so much for being here. We're excited as the Globe Clouds team. Again, my name is Marilei Colon-Robles. I am the lead for the Globe Clouds. And I'm going to be talking to you a little bit about a brief history of this program. We are here at NASA Langley Research Center in Hampton, Virginia. And here at NASA Langley, we've been studying our atmosphere, clouds and aerosols in particular, for over 60 years. And one of the successful instruments is called a CERES instrument. CERES stands for Clouds and the Earth's Radiant Energy System. Now, it's an instrument, not a satellite. So this instrument is on board different satellites. So if you think of the satellite as the car and the instrument as the passengers in the car, CERES has been on board different satellites. The picture on the left I have is the A-train satellite, A for the afternoon, because that's when the satellites pass over the equator around 1:30 p.m. And I want to point out 2 satellites, the Calypso and Aqua. So Aqua has a CERES instrument aboard. Calypso is another instrument here developed at NASA Langley, which is a laser in space, but it's used to determine also clouds and aerosols. So these are some of the instruments here at NASA Langley that we use with the citizen science observations, and then we compare what these instruments on board these satellites see with the observations from the general public. So we actually started this 20 years ago in 1997 when the first CERES instrument went up into orbit. And the program was called the SCHOOL program. SCHOOL stands for Students Cloud Observations Online, and we focus on gathering teachers and students to go outside and do cloud observations. Now again, the CERES instrument looks at the radiant energy, and it has some issues, or sometimes it's difficult for it to detect a thin, wispy cirrus clouds high up in the atmosphere. So this is how we're using the citizen science observations, is to really see what are the observations, the observants, the ground observations seeing, and how does it compare to what we detect with the instrument. As the program grew, right there on the left, there's a cover from some of the first students taking observations. We started getting adults that wanted to also submit their observations. So we call these rovers within the school program. And on the bottom right, you see a picture of Roz Savage. She is the first female to row across the Pacific, Atlantic, and Indian Oceans by herself. And while she was doing this, she was making cloud observations and submitting them to us as she rowed across these oceans. So amazing people making cloud observations. If we fast forward now to 2017, there was an article published in BAMS in March addressing how accurate these crowdsourced data is. In part, they used the school data. So they compared the school matches to MODIS, MODIS being another instrument aboard that Aqua satellite in the picture that I showed before that also looks at clouds. And then what they found is that 87% of the time the satellite and the ground observations from people agreed on the cloud detections. They also compared this MODIS with Calypso, and remember Calypso was near Aqua, and again 87% of the time there was agreement in the observations. If you notice also on the left, that image shows that the program also grew in observations from all around the world, not just in the U.S. So the authors of this paper showed with this finding that this is very robust observations. And what they used then, these observations, is looking at the times when they did not agree. And there is a high percentage when they did not agree based on when there were cirrus clouds. Again, these thin, wispy clouds. Here's an example of this picture. And then in those times, then those ground observations are able to help us validate when the CERES instrument misses these clouds. So really helping out with the algorithm detection. Now, while this all was happening, GLOBE was also celebrating 20 years. And here I have a picture of our former NASA administrator, Charlie Bolden. And this is taken from a video where he's congratulating GLOBE on their successful years. GLOBE stands for Global Learning and Observations to Benefit the Environment. And as the name states, it uses teachers, students, and scientists and citizen scientists to do environmental observations, which include clouds in this case. So what we did was then merge the two programs. So what used to be school in the school team is now known as the NASA Globe Clouds. So we've moved all our things into GLOBE. And this is our main page. This is what it looks like. We have Cloud News, which is a way for us to create engagement with participants. We have teacher guides, how-tos on how to participate, how to see the overpass times when the satellites are going to be overhead, resources, and then ways to contact the whole team in case you have any questions. So during the transition, one of the things that this team here at NASA Langley were able to update within GLOBE were the satellite matching. This is one of the biggest things that this team brought into GLOBE. And really what we do is when you go outside and you do a cloud observation, we look at when did a satellite pass overhead at more or less the same time, and then send you those satellite images. We updated the cloud protocol. The protocol is a way that Globe just calls the steps on how to do the observations to make sure that when researchers use the data, they can compare oranges with oranges. We engage with teachers, the community, and then with the general public with the Globe Observer app. Now we have collaborations from all around the world, and this still includes teachers and students, but it also includes professors in research, but also in education. It also involves professional organizations, after-school and out-of-school time programs as well. Now the Globe Observer app, which started not too long ago, that has been very successful, has allowed us to reach out to now the general public. Some of you guys have used it, particularly for the great North American solar eclipse. This is one of the most successful times that the app was used. So what the app was asking was for people to have some sort of way to determine air temperature and collect observations of temperature and clouds during the solar eclipse. And so due to this, the Globe Observer team was able to collect 76,000 air temperature measurements. And we here at NASA Langley were able to match 19,000 cloud observations, which is really exciting. Here's just a snapshot of the app. Usually we train people or give them tips on how to do cloud observations, but with the app, anyone can download it. So we wanted to make sure in the app that it steps people through how to make the observations. So what the information that we collect is their location, latitude, longitude, their time, and then it walks them through to see if they had any cloud observations or not. If the person says that there were no clouds, then the app then asks them about the sky color. We're looking at the deepest blue of the sky. It looks at visibility, and then it asks for obscuration. So this can be blowing snow, sand, and things like that. If the person did see some clouds, then it walks them through the cloud type and by height. And then it also asks them for the percentage of sky covered by clouds. And if you notice, there's pictures for each one, again, to step them through their observations. If the person has some extra measurements, they can put in temperature, pressure, and relative humidity. And then we ask them for surface conditions, so important for us here. If there's snow, if there's muddy water, standing water, leaves on trees, things like that. Now that's been a brief overview of what we do. Now I'm going to pass it over to Tina Rogerson to talk a little bit more about how we do those satellite matches with the ground observations.
Hello everybody, I am the programmer developer behind the Globe Cloud project. Several of the things that I take care of, one is to provide satellite overpass tools so that our observers know when to go out and do a cloud observation. The satellite data we match to is usually plus or minus 15 minutes when the satellite passes over the given location. We match to various satellites. We match to Aqua, Terra. We match to GO satellites from several different nations, and we also match to Calypso data. All this satellite data is housed at the ASGC, the Langley Atmospheric Science Data Center in Hampton, Virginia. For Aqua matching and Terra matching, for Aqua, we have over 60,000 satellite matches to our cloud observations. And for Terra, we have over 41,000. We also have a lot of ground observations that can match to both Aqua and Terra at the same time. We have almost 4,000 of those matches. This is an example of a table we would send to our user once their observation is matched to satellite data. You can see in the left, the green, that is the ground observation, and the two on the far right, the Aqua and Terra satellite matches. This is an example of a satellite match where on the ground their observation is obscured by blowing snow. But we can see from the satellite that you can see the very low clouds, or the low-level clouds, but there are also mid-level clouds. We also provide the users images of satellite data through Aqua Modus and Worldview, and Terra Modus is Worldview, so that those users can look and see what the satellite image looks like. This is an example of the rapid response lens images that the user would look at to see. Their location is in the center of the observation, so they can look and see what the satellite is seeing while it passes over their location. This is an example of the Worldview application that shows images of what the satellite sees as it passes over their location also. So we provide the observer with a lot of different satellite data so that they get feedback to see what the satellite is seeing compared to what they see on the ground. We also matched Eclipse, which is a much more difficult task. With Eclipse sees a very thin, narrow view as opposed to Aqua and Terra, which sees a much wider view. With Calypso, we are matching a 10-kilometer either side of the overpass, so it's very narrow, and not many schools fall under that location or citizen science locations either. To date, we have a little bit over 500 Calypso satellite matches. When we match to this, what we do is we provide the observer with a browse image that corresponds to their location. This is a browse image that shows clouds at the various levels. We also matched to geostationary satellite data. To date, we have over 88,000 ground observations comparing to the satellite data. The geosatellite data comes from several different countries, the USA, Europe, India, and I can't remember what the other one was. And now I turn it over to our research scientist who is currently using some of this data.
Hi everyone, my name is Brent. I'll be talking a bit about the scientific aspect of this project. So as mentioned previously, this project started off in the education and outreach sector. However, this is intended to be a serious effort to link the education, outreach, and citizen science community with the professional atmospheric science research community. So this effort was started a little while ago, and I was brought onto the team to help continue the effort, carry the torch, if you will. Okay, so I'll be talking about a couple of topics in particular. I'll start off by talking about the general science of globes clouds, the application. And second, I'll be talking about a special topic, which was the 2017 total solar eclipse. Okay, to start with the general science. As this is an effort to link citizen science with professional science. So for a professional scientist, if they're given a new data set, such as globe clouds, they're going to ask two basic fundamental questions about the data. First, they're going to want to know what information about clouds can this new data set, globe clouds, provide that they can't get from other observation systems, such as satellites, surface instrumentation, and so on. most researchers have their favorite data sets, their favorite satellites that they like to use. So what can globe clouds provide for them that they do not already have from their pre-existing observation systems? Second, they'll want to know about the validation of the globe clouds data. Can the globe clouds data be trusted? It's a very important and question to address. And there has been some work done already, but again, I was brought on to help continue that work. So we are currently in the beginning stages of working with the scientific aspect of globe clouds data. So at the moment, I don't have any awesome results to show you guys, but I can talk a bit about the kinds of topics that we're going to be focusing on. So the first meteorological situation we're interested in, as mentioned earlier, are the question of observing thin cirrus clouds or subvisible cirrus. As mentioned earlier, many satellites, including Ceres, have difficulty detecting these thin cirrus clouds. Now, there are a couple of satellites that were designed specifically to detect thin cirrus, namely Calypso. However, Calypso has limited sampling. It only sees at certain times of day. It has a very narrow swath. And so, you know, as great as a satellite as it is, it has its limitations. So we are planning to use globe clouds data to fill in the gaps of where Calypso and other satellites cannot see. The next topic is contrails. These are contrails left by jet aircraft. You see them quite commonly over most of the U.S., of course. And these are of scientific interest because they have a small but non-negligible effect on the global energy budget. So these are difficult to detect by most satellites. There are a couple of high-resolution imagers that can fairly reliably detect them. But again, more eyes on the ground looking for these things will help fill the gaps in those satellites. So Kaylee is going to be talking a bit more about this particular topic. Finally, as mentioned earlier, there's the issue of observing low clouds that occur below high cloud layers or aerosol layers. Pretty much all passive remote satellites, those are satellites that don't carry a LiDAR, laser, or a radar, or things like that. Passive satellites generally can't detect low clouds occurring below high clouds or high aerosol layers. And so the passive remote sensing community has to use basically guesstimates to figure out how often these multiple cloud layers occur. So again, there are certain satellites like Calypso and CloudSat that can help see some of these situations, but again, they have limitations in their ability to observe all of the situations. So we would like to use globe clouds data to help fill in the gaps in the observations. Okay, moving on to the second topic, I'm going to be talking about a bit about the Great American Total Solar Eclipse of 2017. I'm sure many of you guys and gals went out to see at least some portion of this eclipse, and of course there are many awesome photos and composites and so on put together over about the eclipse. This is one of my favorites. Okay, as a general overview of globe clouds, looking at this eclipse, as mentioned earlier, there were 76,000 temperature observations and 19,000 cloud observations gathered by 17,500 unique observers. And I mentioned temperature observations because we asked the observers in the fields to buy and carry their own thermometers out to record the temperature change over the course of the eclipse. Now, shown here is a schematic of all of the unique observers. And you can see that this is the path of the eclipse here of the umbral shadow where the moon completely blocks the sun. And you can see that many of the observers thankfully chose to line up along the path of totality, which is really helpful for us because they can see the whole event, which pre-existing automated temperature observing stations obviously can't move into the path of the shadow. So this was able to give us lots and lots of observations of the meteorology in the path of totality. Okay, so I've put together a short video of just summarizing the event, and let's see, we're going to bring it up. Okay, so you'll see here each frame is 1 minute with all of the temperature observations taken by globe cloud observers, and this goes as the eclipse progresses. You can see the lunar shadow moving over the United States, and as it passes over, people have lined up in the path of totality and are taking a bunch of temperature observations. And as the lunar shadow leaves, everyone goes home, gets caught in traffic jams, and all sorts of other fun. Okay. All right, thank you. Okay, so what we can do, you saw all of the observations. What we can do is take the observations from each unique observer and create a time series of the eclipse event. Where is the pointer? There it is. Okay. All right, so here on the left, you can see the time series of the raw temperature. The x-axis is the UTC hour, and the y-axis is temperature, and that should be degrees Fahrenheit, excuse me. And so this looks like a big mass of spaghetti, as you might expect, because these are temperature observations taken all over the United States. However, even here you can see that around 17 to 18 UTC there appears to be some sort of decrease in the temperature, which is a signal of the temperature depression caused by the solar eclipse event. Now, we don't want this to look like spaghetti, so what we can do is remove the mean temperature observed by each observer to get the temperature change over the course of the day as seen by each observer. So I'm showing that here in the middle. The mean temperature has been removed, so this is a temperature change over the course of the day. Now, the eclipse occurred around mid-morning to early afternoon, or late morning to early afternoon, so you would expect normally that the temperature should rise, as shown by the black line here, but continue to rise and peak later on in the day. However, you can see that the mean temperature observed by the black line is the mean temperature observed by all of the observers, the mean temperature change over the course of the day, I should say. You can see that there was a decrease in the temperature caused by the eclipse here. However, this temperature decrease is smeared over the course of a couple of hours because the eclipse occurred over the course of several hours. So what we can do is align these temperature time series relative to the time of maximum obscuration, or for the people on the path of totality, the time of totality, when the sun was completely covered. So if we do that, we can see that the citizen scientists observed a significant decrease in temperature occurring shortly after the time of maximum obscuration. The numbers here, for all observers, they saw a temperature decrease on average of 4.1 degrees Fahrenheit, which occurred about 13 minutes after the time of maximum obscuration, or after the time of totality for people in the path. So how do these numbers compare to what what scientists in the past have seen? So here I'm showing a table taken from a summary paper written in 1999 that shows the temperature depression caused by eclipses in the past, as seen by pre-existing meteorological stations, and also the relative time of the minimum after the time of maximum obscuration, or the time of totality for people in the past. So you keep in mind that these temperatures are given in degrees Celsius here instead of Fahrenheit. Scientists tend to talk in Celsius instead of Fahrenheit, but you can see that the range of temperatures seen by scientists in the past are about half a degree Celsius or 1 degree Fahrenheit to about 10 or so degrees Celsius or about 20 degrees Fahrenheit. So our observations are on the lower end of what people have seen in the past. However, this is consistent with the citizen scientists of our event observing in both clear and cloudy conditions, where clouds tend to reduce the temperature depression caused by the eclipse. What's particularly interesting is that if you look at this column, you can see the time of the relative time of the maximum temperature depression caused by the eclipse, right after the time of maximum obscuration, or the time after mid-eclipse. And you can see here the times range from about 5 minutes to about 15, maybe 20 minutes after the time of maximum obscuration, which we saw 13 minutes. So we're right in the ballpark of what scientists in the past have observed, which means that the globe cloud citizen scientists were able to capture the meteorology of the event. Even though this was a somewhat experimental, a new thing to do with citizen scientists, to some extent it worked, and we're able to see the meteorology of the event and be able to gather some useful scientific information about the meteorology of the eclipse. Well, as you might expect, because this was a somewhat new thing we were trying, there are some discrepancies in the temperature observations that we are looking into cleaning up the data so that we can get a better quantitative estimate of the meteorology of the event. So here I'm showing a still from the video that I showed earlier, and you can see this is right in the middle of the eclipse passing over the United States. And I'd like to draw your attention here to Oklahoma. If you look at Oklahoma, for example, you see that there are 3 observers at this particular time which saw a temperature of something, or they reported a temperature, I should say, of something like 85 degrees Fahrenheit. However, there's one person here who's recorded a temperature of about 75 degrees Fahrenheit or so. That's suspicious. We don't expect a temperature difference across the state of Oklahoma to be that large over the eclipse event. So this particular observation probably has an error of some kind involved. There are other places around the U.S. that you can look at as well. You might look at southeast Texas, for example. This is middle of the day, middle of August. You probably don't expect a temperature of 75 to 80 degrees Fahrenheit occurring in Houston at this particular time. So this person probably, there's an error of some kind here in this temperature observation. So what sort of causes for these type of discrepancies have we found so far? Well, we've identified a couple of important ones. First, the observers were asked to report whether their temperature measurement was in degrees Fahrenheit or degrees Celsius. We think that there was a few cases where people reported the wrong temperature units. So there might be some basic unit conversion errors in here. And we're currently working on ways to identify these situations. Second, it seems that a few people chose, instead of bringing their own thermometer into the field, which we really would have liked them to do, they just read the temperature off of their smartphone instead and recorded that, which the temperature from the smartphone, for those who don't know, usually comes from National Weather Service data. So that's just telling us what the Weather Service saw, which we can already gather that data from other places. So we're working on ways to identify how to clean up the data and remove those kinds of discrepancies. I don't have time to go into it in detail, but we're looking at ways to use National Weather Service data and local state mesonet data to help us identify these type of temperature discrepancies and clean up the data as a result. Okay, so once we clean up the data, we know there is a signal. We know that the citizen scientists actually observed the meteorology of the situation. So what sort of scientific questions can we address using the globe clouds data? Well, first we can look at the relationship between the cloud cover occurring at each observer's location and the temperature depression or decrease that they observed caused by the eclipse. We've seen in the past that the more clouds there are at a location, the lower the temperature decrease at that location caused by the eclipse. So this event is nice for the citizen science data because many of them recorded both the temperature changes over the course of the event and the cloud conditions over the course of the event. And so we can combine those to see how did clouds affect the temperature change. And we have some very preliminary results showing that indeed there is an effect, that the cloudier the scene was for a given observer, the smaller the temperature decrease that they observed. But again, we're working on cleaning up the data and getting a better quantitative estimate of that sensitivity to cloudiness. Second, we can look at the variation in temperature and the temperature decrease caused by the eclipse in regions that don't have dense pre-existing observation networks, such as mesonets. I didn't get a chance to show it, but there are many states, such as Oklahoma, that have very dense observation networks that recorded the temperature change of the event. So you might be asking, why not just use the pre-existing temperature observing networks to capture the meteorology of the event? Well, there are places, for example, out in the American West, where the temperature network is not nearly as dense as in places like Oklahoma. So, as I showed earlier, many of the citizen scientists decided to line up, fortunately, along the path of totality, so we can use those observations to cover the gaps in the temperature observations from previously existing observation networks. So that's a very useful benefit of the globe clouds data in helping to understand the eclipse. So finally, I'll mention that we're working with other members of the, we here at NASA Langley are working with other members of the Globe Observer team to help explore the globe data and determine its robustness and the scientific utility of the observations, in particular with the eclipse event. All right, so I'll turn it over to Kaylee, who will talk about the use of neural networks with globe clouds data.
Hello everyone, my name is Kaylee Dantas and I'm a graduate student intern here at NASA Langley with the Globe Clouds team. Specifically, I'm with the NASA Internships, Fellowships, and Scholarships program. I'll be talking today about some use of neural networks in the globe clouds, specifically the globe observer data. So a little bit about my background. I'm really interested in math. As you can see, my undergraduate degree is in mathematics and my current graduate studies are in applied math. So I'm fairly interested in looking at ways that we can use computer vision, so object detection, which is a subset of artificial intelligence, graphical models, and image segmentation techniques on the globe observer data, specifically the images that we receive from the cloud observations. So with the growth of the Globe Observer program, as we mentioned earlier, the Globe Observer mobile application, which is available from the App Store on your phone or tablet, it is available to anybody. So we have a large community of citizen scientists, teachers, educators, students, and general public that have been joining the community of citizen science and cloud observers since 2016. So we're currently active in over 119 countries, and we, as of October of 2017, we had over 71,000 registered users. So in addition to the growth of the platform, that we've had a large number of sustained users. So with the Eclipse in 2017, we saw a huge spike, and we've seen that people are still interested in submitting cloud observations. So with that, the question that I came in asking is, how can we validate the data in a way that's effective for on a large scale, and how can we engage this community of citizen scientists and cloud observers and hopefully promote STEM engagement? So with that, I decided that using artificial intelligence would be a great way to introduce new technology into the platform. The figure that you see here is just an image of the Globe Observer program that Marilei showed earlier. You can make cloud observations directly from your phone, and the images that it's scrolling through here are just some of the steps that you can take as an observer to submit your observation. So what we see here are, in addition to the measurements that users will submit with their cloud observation, they also have the option of submitting photos. These are very useful for us because they not only provide some validation for the user's observation, but it's a great way for us to look through the Globe visualization tool at the images submitted from around the world. So the image that you see here is a picture of from Redmond, Washington, that a Globe observer submitted. We see some contrails, some cirrus clouds, and these are clouds that are specifically difficult to detect from the satellite view. So an image like this that would be submitted to us would be of great value if we can extract the cloud types in the image. We currently do not receive or report the cloud types that the user saw in the satellite match report. So if there's a way that we can provide further enhanced feedback to the user, that would be really great. So an image like you would see here, if we put this through the algorithm that's in development, we would output something like this. So it has bounding box regions around the different cloud instances, as well as, most importantly, a cloud proposal, so a cloud type proposal. So oftentimes, as end users will submit their observations and we will generate a satellite match report, users will often wonder if their observation was incorrect, if there was a discrepancy between what the satellite saw and what they reported. In this way, we would be able to say that there was a discrepancy based on either hopefully user error or if it's just the case that the satellite wasn't able to see a high cirrus cloud or a contrail. That will hopefully allow users to make more informed observations in the future. So with this, a few technical details. So with object detection, we have to do a number of image pre-processing steps. If those of you that are familiar with signal processing, we use a lot of foreground subtraction techniques. Things like this will be performed before the image is fed into the neural network. And once it is fed into the network, it will output the bounding box proposal, the little yellow box that you saw in the previous slide, as well as the cloud type proposal. So some of the benefits to introducing this technology into the Globe platform is that it will hopefully provide enhanced validation both for us as researchers and for users so that they can make more informed observations. Also providing feedback to users, because we may not necessarily directly communicate each person's the results of the satellite match. So hopefully this is a way that they can engage more with the cloud match process. And finally, this is a nice way to introduce artificial intelligence and new technologies into the Globe Observer and Globe Clouds platform. So with that, I'm going to be passing it back over to Marilei, and she will tell you more about how you can reach us at the Globe website.
Thank you so much, Kaylee. And I hope you all are excited about this data set and about this program, the Globe Observer app. All this data is available on the Globe site, www.globe.gov. When you hover your mouse over the portion of the site that's called Globe Data, this will pop up. And I just want to point out two things here, the visualize data and the retrieve data options. These are options to see the data that's available. So looking at the visualization system of data, the first option here, this is a snapshot of what you would see. There's a place here where you can choose the data set. Clouds are under atmosphere, so I choose looking at all cloud types for a distinct time portion of time, and you see that every single dot is a cloud observation. I want to point out these are very interesting observations, particularly these right here are some science expedition cruises that go to the Antarctica. So these are great observations for scientists right over the ocean. So this is a group that can be called upon to do some observations for a particular time period or a particular location. Again, this visualization system is great to see where the data is. The second option, the Advanced Data Access Tool, then it's a great way to download the data. You have options here, it's not shown, but you have options to choosing your latitude and longitude of a particular location for a particular protocol or observation type, and then you can easily download all this data available. So currently we're having a data challenge. It'll run from March 15th through April 15. I hope that you all participate. What we ask is for cloud observations, and the people that submit the most observations through Globe or Globe Observer will get a nice shout out from a NASA scientist that uses cloud observations. So it'll be really exciting. You can go to the Globe site, but you can also contact us as the Globe Clouds team. We'll be more than happy to answer any questions down the road, or you can contact me directly. So we're really excited about hopefully hearing from you. So with that, I'm going to turn it back to Jennifer.
Okay, great. Thank you, Marilei. So at this point, what we'll do is we'll move to our final set of polling questions. I'll give these questions just a couple of minutes or so, and then we will jump right into the Q&A. And we appreciate your feedback on this. So we'll give these a couple of minutes, and then we'll move on to the Q&A session. Thank you. Okay, everybody. We're going to go ahead and jump into the Q&A session here, but certainly if you think of something regarding the polling questions, feel free to enter that into the Q&A pod. If you're interested in more information and you didn't have an opportunity to write down your email address, you can always feel free to contact me directly as well, or any of the members of the GLOBE team, and they'll be able to get in contact with you. All right, so with that, let's move to our very first question here. Just give me a second. Our first question is, how quickly is a cloud image analyzed? Is it something that could be provided back near real time to the observer within the app?
Is this question referring to the work that Kaylee is doing, or for the satellite matching?
So if the participant, Kristen, if you could provide clarification, that would be helpful. Yes, what Kaylee is doing. That's right. Thank you.
So thanks, Kristen, for the question. So currently the algorithm is being designed to be implemented during the satellite match process. It would be something that Tina would generate. If further down the road, this seems like it's a very popular portion of our satellite match, and we can see about ways of building it into the app. There's some really interesting things that I know that Google and other large AI companies have done to build this into real time. But currently it is designed to be implemented during the satellite match phase. And Tina can speak more to the time in which it takes to create the satellite match in terms of how long it takes to match to each satellite, but that is all that I have for this point.
Okay, thank you, Kaylee. All right, so our next question is coming from south of Brazil. We are working with citizen science in the south of Brazil. Soil activities. How can we engage people in our activities since we don't have a name like NASA? So do either of you have some feedback on this?
That's an interesting question. One of the things that we strive here when we engage the public is to make sure to point out their role in the program, so really highlighting their importance, their contribution, and the why. So that might be already happening, but really focusing on that and maybe putting into with activities, maybe some hands-on activities that show the with and without their observations might be interesting for them to see how important they are. I think Brent also has a comment to add.
So recently there was a satellite launch called SMAP, and I don't remember what that stands for. No, wait, I do remember. It stands for Soil Moisture Active Passive, which it's designed, as it sounds like, to measure soil moisture over most of the planet. So we here are looking at matching globe data with cloud observing satellites. I think there's a similar program that you could be doing to matching the soil moisture observations with the satellite, the SMAP data. I'm just talking as I think here, but that seems like a good possibility, something to look into for the future.
Okay, great. Are there any additional questions? While we're waiting to see if there are additional questions, I just wanted to point out that we have today's presentation files. You'll find them in the file sharing pod located in the lower right-hand corner of your screen. So here you'll find the MP4. The Eclipse observations video has been uploaded there. The presentation is there as well, both in PDF format as well as PowerPoint. And then finally, the agenda. So if you're interested in downloading any of the files, what you'll do is just highlight any of those, and you should be prompted with an option to download the file. And you are welcome for the response. Are there any additional questions at this time? Buddy? Okay, well, we'll give it just another minute or two. And what we'll do today, if we don't have any additional questions, what I'll do is I will log off from the audio component of the webinar, but I will leave the virtual meeting space open. So if you think of something, please feel free to enter that into the Q&A pods. I will provide all of the feedback to our presenters, so they'll certainly be able to follow up with you offline. And I'd like to thank all of you for joining us today. Let's see here, just checking again. I don't see any additional questions. Additional questions? Going once. Okay, here we are. Okay, so let's see. The question is, how can you validate pictures sent by people since they can send any photo? That's a very good question.
So thanks for the question. This is a very, actually, I could speak to this for hours, but so one of the great things about the Globe Observer app is that when the user is uploading the images, while they do have the option to manually upload them, the in-app camera actually captures the images from 6 different directions automatically. So north, south, east, west, up, and down orientations. And for the most part, we do see that people orient their phone, looking at the sky. Images are also, I guess, when users submit them, there is a process that Globe will take to make sure that the image doesn't contain anything that doesn't belong in there. But in the sense of feeding it into the algorithm, there is a big chunk of the work that the algorithm does is to do what we call foreground subtraction. So in that sense, we have to denoise things that are in the foreground, meaning cars, buildings, trees, and so on. So part of the legwork of this algorithm is that it will denoise those high-frequency signals in the foreground so that we can therefore get a better picture of, literally, of what is in the background, meaning clouds. So the great thing about region-based convolutional neural nets is that they allow us to search over the image space in its entirety. So rather than just doing scene detection, meaning that we assign a single label or a class of labels to the image, we actually search over the image to specify where that object is actually located in the image. So that provides a sense of further validation within the algorithm because we know that we can actually see what the algorithm is pointing to. But there is a fair amount of work that goes into the pre-processing stage that requires us to basically denoise certain parts of the image. So thank you for your question.
Okay, fantastic. Thank you, Kaylee. Are there additional questions? You're welcome. I also wanted to mention that the SMAP data, we have an application that was also mentioned, I think by Tina, NASA Worldview. So SMAP, soil moisture, root zone soil moisture data is actually available as a layer within our NASA Worldview application. And I can type that link in a second for Alexandra. And then we do have an additional question here. The question is, are there types of clouds that are proving harder to identify?
And thank you for this question as well. Actually, the technology that goes into image detection from the ground observer is really actually similar to that satellites use. We do, however, have a better view from the ground. So in that sense, clouds with poor boundary definition are more difficult to detect. So Interestingly, contrails are really easy to see because they have a really nice defined edge. So a lot of the algorithm is using edge detection. So in that sense, clouds that are multi-layered, stratus clouds mostly, it's difficult to detect the different cloud layers. That is definitely the biggest challenge when identifying cloud types. Cumulus clouds are really easy to see because not only do they have nicely defined edges, but generally they occur there's a nice contrast in color between the sky and the cloud color. So really bright white clouds are much easier to detect than low stratus clouds.
Okay, excellent. Thank you. Any additional questions at this point? Okay. All right. If there are no additional questions, what we'll do again, we'll leave the virtual meeting space open and we'll log off from the audio component. For those of you, oh, hold on a second, we do have a question just came in. After submitting a photo, is there a way for an interested citizen scientist to see the results of the AI algorithm or get involved in any way with the testing and development of the algorithm?
Thanks for this question as well. So I'm going to answer this in two parts. So within the testing or development phase, currently that's not something that we're necessarily doing, but I'm sure that if this project expands into something larger than just an internship project, there may be opportunities for beta testing and such. But in regards to the result of the algorithm, the cloud type will be if the user submits an image along with their along with their cloud observations, that can be pulled from the GLOBE database. And so when Tina is creating a satellite match report, she'd be able to pull that image and run the algorithm so that in that way, in addition to the information that you've seen in the match tables, we'll also be able to include the user's image with the object proposals and the cloud type proposals.
Okay, very good. Thank you, Kaylee. All right. Okay, if there are no further questions, we'll log off from the audio component and we'll leave the virtual meeting space open. And I'd like to thank our speakers today, as well as all of you for participating in today's webinar. For those that may be interested, we do have a webinar on March 7th that will focus on International Space Station lightning data. So if you're interested in if you're a scientist and you're using data, that is something coming up next week. All right. Well, thanks, everybody. We'll leave the virtual meeting space open, and I hope to see you at an upcoming webinar. All right. Bye, everybody. Thank you, speakers.